So there's a bee on this slide, and you might be wondering, how does this involve mechanisms? Well, I love a good example, and pollen sticks to this bee due to electrostatic attraction. When it flies, a bee loses electrons and it builds up positive electrical charge, and then the flower's pollen, on the other hand, is negatively charged. So when the bee lands, the pollen experiences a driving force from the flower to the bee because we have those electrostatic interactions. Similarly, the elementary steps we examine in Chapter 7 are driven by the flow of electrons from a site with excess negative charge towards a site with excess positive charge. Now, in Chapter 6, we learn that a proton transfer is an elementary step. It occurs as a single event. Frequently, however, a proton transfer makes up one step of a multi-step mechanism, something we're going to discuss more extensively in Chapter 8 and honestly through the rest of organic chemistry. There are a handful of other quite common elementary steps too, which can be combined in various different ways to produce mechanisms for numerous reactions. The 9 new elementary steps that we're going to learn in this chapter, along with the proton transfer steps, which are 10 in all, make up nearly all the reaction mechanisms you'll encounter through Chapter 25. Knowing that the same 10 elementary steps make up the mechanism for many reactions, you can be confident that mechanisms simplify organic chemistry. The time and effort you spend mastering these elementary steps in this chapter will be rewarded as you continue to learn reactions through the rest of the book. Keep in mind that this chapter serves to provide an overview of the common elementary steps. Later chapters will describe in more detail the central roles these elementary steps play in more complex mechanisms. For now, your goal is to learn just 3 aspects of each elementary step: the types of species, that are required, as the reactants and products, the curved arrows, that describe the electron movement, which are really the bonds breaking and making, and 3, the driving force of the reactions. Think of Chapter 7 as a summary. Think of the Chapter 7 summary as a reference to be revisited frequently, not only as you make your way through this chapter, but also when you encounter these elementary steps in reaction mechanisms in later chapters. General forms of all 10 elementary steps are described in the chapter summary on page 350 through 351. I really want to encourage you to start looking at these chapter summaries of all the mechanisms that we're going to encounter. And so this is, I think, one of the best, just one of the best materials that this book provides. So do take a look at that. As a matter of fact, you may want to photocopy it or print it. So without further ado, let's kind of jump right in. Curved arrow notation was introduced in section 6.1 as a means for keeping track of valence electrons in an elementary step. It can be far more powerful than that if we recall 2 concepts. The first concept that we need to recall is that opposite charges attract. Just like magnets. And then like charges repel. Okay? And then the second big thing we need to remember is that atoms in the first and second row of the periodic table must obey the duet and octet rules. That means you cannot have any expanded octets, right? So these atoms, first and second rows there, are only going to have either 2 electrons, for example, in the case of hydrogen, or 8 electrons around them, for example, in the case of carbon or nitrogen. So I want us to look at the mechanism shown here in 7.1. I want you to notice that the OH bears a negative charge, and that's shown here. This is a really electron-rich site. There's lots and lots and lots of electron density here. I want you to notice that in HCl, the chlorine is really, really electronegative. It's going to withdraw all this electron density over here to the chlorine. And what you're going to see is when it withdraws that electron density to the chlorine, it makes this hydrogen partially positive. So what we have here is a negative electron-rich site, and these electrons come out and they attack that proton, and they're going to pull that proton back to form this new bond here. The electrons that make up the hydrogen and chlorine bond are then going to go on to the chlorine. So it just breaks apart and they go there. Now, chlorine is also partially negative, but it wouldn't make sense for us for the electrons to come over here and attack the chlorine because those have like charges and like charges repel. So it only makes sense for these electrons to come and attack the partially positive hydrogen. Now, so I want you to remember in an elementary step, right, such as the one shown here, electrons flow from electron-rich sites, things that are negative, right, or partially negative, to electron-poor sites. These will be things that are positive or partially positive. The other type of electron-poor site that you have besides positive or partially positive is one that lacks an octet. So that's also an electron-poor site. Now, so that kind of summarizes what we looked at with the arrows. I want you to notice that the curved arrow here on the left is representing the flow of electrons from this electron-rich site to an electron-poor site. It's showing the movement of these electrons, not the movement of the atoms. So let's do an example. Okay. Identify the electron-poor hydrogen atom in methanol. Draw a mechanism by which methanol acts as an acid in a proton transfer reaction with H2N-. So here's some things to consider. What kinds of charges characterize electron-poor atoms? Which hydrogen in methanol bears that kind of charge? So when we think about this, an electron-poor atom tends to have a partial or full positive charge, right? So it's going to have a partial positive or full positive charge. Because the oxygen in methanol is really, really electronegative, right? So this guy here is really electronegative. The attached hydrogen here is going to bear a substantial partial positive charge because this oxygen is going to, because it's so electronegative, it wants to pull electrons towards it. It's going to pull these electrons this way, leaving a partial positive charge here. Okay. So we've identified the electron-poor hydrogen atom in methanol. That's the first step. So let's look now. We're going to draw the mechanism by which methanol acts as an acid in a proton transfer reaction with H2N-. So when we look at methanol, okay? We know that this is the acidic hydrogen. And so now we've got to figure out how it's going to react with H2N minus. So NH2, and then we're going to put those electrons around to give us that formal -1 charge. And we have to show that minus, and we've got to show the electrons. So should H2N minus be considered electron rich or electron poor? It has a negative charge, so it should be considered as something that's electron rich. Then what you need to consider is when H2N and CH3OH are combined, how do we draw a curved arrow to depict the flow of electrons from electron-rich site to an electron-poor site? Well, so we're going to draw a curved arrow from the electrons on nitrogen, right, because that's where that electron density is. So we're going to start where the electrons are, here, to that hydrogen. And those electrons are going to pull that hydrogen back. And so I like to go ahead and draw that hydrogen being pulled back, right? So that's the new bond that we formed. And those electrons that are shown here with the red arrow that come out here, they form the bond right here, okay? And then, right, when we look at this, so we've drawn the first part here, okay, and we form this new nitrogen-hydrogen bond. The second question that we need to ask ourselves is, or the fourth question, I guess, when that curved arrow is drawn to depict bond formation, do any other bonds have to break? Well, when this hydrogen gets pulled over here, this bond breaks. And those electrons go here on the oxygen. So that initial OH bond must break. And so when you draw now, nothing has changed between these carbons and hydrogens, but now we have these extra electrons on the oxygen, and when oxygen has one bond and 6 pairs of electrons, it carries a negative formal charge. And so we've shown how to draw the arrows in this proton transfer reaction. Now, we need to go over a few other things before we jump into the rest of the mechanisms. So, contrary to what's suggested here in equation 7.1, we can't simply add a hydroxide anion to HCl to carry out the proton transfer reaction, because anions do not exist in the liquid or solid phase without the presence of cations, right? Or vice versa. So you can't have a cation without an anion. However, we can add a source of OH. Right? Such as sodium hydroxide, right? Sodium hydroxide is an ionic compound, so in solution, when we dissolve it, it's going to form Na plus and OH minus, right? Dealing with sodium hydroxide, rather than just OH minus, may at first seem to complicate the picture because Na plus is electron poor. And so we would automatically think that maybe sodium would react with an electron-rich site of another species. As it turns out, sodium behaves right here as a spectator ion. And that just means it's not going to take part in a chemical reaction in solution, just like we learned in general chemistry. So sodium's not going to affect this reaction in any way. It's why if you need a source of hydroxide, sodium hydroxide is a good source to add. So let's look at an example. Draw the necessary curved arrows for the proton transfer between KOCH3 and HCN in solution. And so here are some questions that you need to ask yourself. In KOCH3, what can be treated as a spectator ion? Generally, if you have any group 1 metals in general, they can be treated as a spectator ion. This would be like sodium or potassium. So the very first thing you need to do is identify the things that are ionic. So KOH3 is ionic, right? And so that means it's made of K plus and OCH3 minus. And so we can treat K plus as the spectator ion because it's a group 1A metal. Then by disregarding K plus, we consider just OCH3 as the reactive species that's going to remain in solution. So just OCH3 minus is going to remain in solution, and it's going to bear a full negative charge, so we can go ahead and consider that as the electron-rich species. So, which hydrogen should be considered electron poor, and how should the curved arrows be added? So if we have CHHO minus plus HC N, okay, when we look at this, the carbon and nitrogen there are fairly electronegative, so this proton is going to be the one that's electropositive, so that's going to be the electron poor site, right? It's also the only hydrogen there. So how should the curved arrows be added? Well, we're going to draw curved arrows from the electrons, which are electron rich, to that hydrogen, which is electron poor. When we do that, the HC bond is broken, and so those electrons are going to go right there on the carbon. And so what we form is methanol, and then cyanide ion. There. So this would be the mechanism with the curved arrows. Now, so we've made some assumptions with our group 1 metals. We've talked about spectator ions. Analogously, we can also make simplifying assumptions for reactions involving organometallic compounds. Organometallic compounds, right, have a metal atom bonded directly to a carbon atom. Okay. Examples of organometallic compounds include alkyl lithium, alkyl magnesium halide, which are also called Grignard reagents. And we're going to look at more Grignard reagents in the next page. And then a lithium dialkyl cuprit ion. These kinds of organometallic compounds are going to be really super useful reagents for forming new carbon-carbon bonds, which we're going to discuss in Chapter 11. So, what we find here is that the carbon metal bond acts as a polar covalent bond. And so what happens is carbon is more electronegative than the metal. And so because of this, organometallic compounds can simply be treated as electron-rich carb anions, right? And so I want you to know the definition of a carb anion. That's a compound where the negative charge is on the carbon, right? So, I think I want you to, just in summary, organometallic compounds include alkyl lithium, which are a lot of times shown as just an R group bonded to lithium. They include alkyl magnesium, halides, and that's a lot of times shown as RMGX, where X is a halide. These are also called Grignard reagents. That's a really common name for those. And then lithium dialkyl cuprates, which are shown as lithium with a positive charge, and then 2 R groups on a copper and that gives that a negative charge. So when we consider organometallic compounds in the flow of electrons from an electron-rich to an electron-poor site, we often leave the metal as the spectator ion. And so we can simplify it just down to the carbanion ion. I want to show you some examples of this on the next slide. So these are examples of the different organometallic compounds that you can see. This is an alkyl lithium compound. And you can see we've simplified it. We've dropped the lithium, kind of like a spectator ion, and have just added the 2 electrons here to the carbanion ion, and we know that this is electron rich. This is a Grignard reagent, and so we're going to drop this metal part and just add these electrons here to show that this is electron rich. Here is that lithium cuprate compound that we have. We are going to drop this entire part here, right? Because it's just this part here that forms the carbanion ion. So hopefully this helps you kind of visualize what we talked about on the last slide. The last thing that we're going to talk about in this screencast are hydride reagents, because we're going to make some simplifications with them as well. Hydride reagents commonly function as reducing agents. So organometallic compounds or organic compounds can undergo oxidation reduction reactions. And so hydride reagents are used in those oxidation reduction reactions where they cause something to be reduced. And common hydride reagents are lithium aluminum hydride and sodium borohydride. And we can see their full forms here, but we just can simplify them. So first off, we drop either the lithium or the sodium, right? And so we can simplify them to here, but more often people simplify them either farther to just show the hydrogen with those electrons and the negative charge. This is interesting historically, because historically people will still keep these and just show the mechanism like this, where these electrons are leaving, but more recently we've just shortened it to this hydrogen. So this hydride. I said hydrogen, and that's so wrong. Hydride. So let me separate these out for you. Hydrogen has 1 electron. Hydrogen, right? A proton has no electrons. That's a proton. A hydride has 2 electrons and a negative charge. Don't be me. Call that a hydride. All right, so that ends our first screencast, where we really talked through section 7.1, where we looked at kind of some simplifications that we can make with mechanisms, and then identified some language that we're going to use. In section 7.2, we are going to start looking at nucleophilic substitution steps and talk more about different types of mechanisms that you're going to encounter.